I'm glad I put model in my talk title. So it's such a great feeling for me to come back to here to speak. About 20 years ago, that was my first time stepped into this building and starting my actually completely new life, new journey. So as Dr. Baras was just mentioning, my PhD work was on hysteresis. In particular, I worked on this so-called magneto-restrictive material and the magneto-restrictive actuators. Krishna, I hope you still have that in your lab.
It's gone through some transformations when you come see.
All right. So, so a lot of work has been associated with these loops we call hysteresis loops. And of course, I'm not going to get into detail of my PhD discussion, do another PhD defense here. But what I would like to do is for the next few slides, because I know some of you are students or starting faculty member, just to give you a sample of some of my research activities. Maybe that's just one example of how your PhD research can serve as a root, and you grow your program from there in different directions. So when I started, a lot of people give me advice, say, okay, you cannot just do the same stuff like your PhD research because you will not be able to detach from your PhD advisor. So I thought, okay, what should I do? Maybe modeling and control of smart materials was my research topic when I was a student. I can do something similar, but it's different material. So I ended up choosing something called electroactive polymers. These are polymers that are active once you apply voltage, for example, and they can move, bend, so serve as actuators, but they can also serve as sensors. So just give you a quick example. So this is one material that at that time I purchased, and then from a company, startup company, and then we did modeling and control. Actually, I had my career grant on this topic. And from there, we have actually, over the years, my lab has started making these materials, and Frank knows very well. In the recent collaboration with Derek Haley's group and a few others, my role actually is to produce these materials and devices. So I don't even have a role to play in terms of modeling and control there. So in this particular project, we're using these materials as sensors for like underwater robots, which is mimicking so-called lateral line for fish. These are arrays. So this, you're looking at a giant Daniel fish, the front image here. And all these highlighted dots are so-called neural maps for lateral lines for sensing flow. So we have created, actually I'm glad Frank is here, I think he was involved in some of these experiments. This is a actuator robot that is going to orient itself upstream along the flow direction, which you cannot tell because water is transparent here. But based upon these whiskers, I don't know whether you can tell from the picture here. Let me try to, okay, you cannot quite see. So these are the whiskers. These sensors provide sensor feedback, and then Derek's group actually use that to estimate the flow information, and then in this case close the loop by orienting the robot upstream of water. So that's one kind of topic, and then from there on, of course, now we know software robotics is very, very hot area, and we have been involved since this electroactive polymer stuff, the sensors and actuators. And for this particular thing here, we're interested in, for example, stiff tuning materials, because stiff tuning is very important for software robots. You want the robots to be able to navigate through narrow openings or very curvy channels. But sometimes you also want the robots to be able to sustain loads, which means you need to be able to stiffen up. So in this case, I'm showing one example where we have a 3D printed material which is showing as black here. When it's heated up, so it's 3D printed but also it's conductive. So I can just apply current to heat it up. at any select points, and then when it's heated up over so-called glass transition temperature, it softens. All right, so a pneumatic actuator like this, without this black layer, would just bend with a uniform curvature, but now because of this black layer, which usually is stiff, so it's constrained, and I can selectively let portions of that to be soft, so that you can bend at those locations, we call virtual joints. This right video shows that idea. So in this case, I have three these joints. When I turn on this one, which means I apply current there, you see the curvature happens at that particular point. And if I turn on everybody, then of course it turns at those joints. So why is this useful? So as I just said, well, stiffness, like now actually if I turn off this, it keeps the stiffness so that it maintains the structure, kind of load-bearing structure. So it's useful to be able to tune the stiffness, but also actually I just use this to shape control, right? So by applying stiffness tuning, actually I was able to do shape control. And one of the things that we are exploring with a number of collaborators is to create soft robots that are able to navigate in, for example, in narrow channels of human body to deliver detection devices or therapeutic devices. And in there, you have to be able to manipulate, articulate, along different, to comply with the constraints of the path, and also being able to do it in a sort of autonomous manner. So this shows one prototype where this is actually a pneumatic actuator with 3 chambers. Actually, it can bend in different directions. And as a test, kind of preliminary test, we put this into MRI machine where we actuate this robot, and then we can look at the slices of the MRI images, and from that we get a 3D reconstruction from which we will extract, for example, the local channels and the curvature information, which will be used for feedback control of the robot when it's ultimately inside a human body, for example, cavity like GI tract. So, robotic fish, how is that? Why did we start on that? It's also because of the material that I just mentioned, and some of you have seen this video before. Essentially, we start off with an outreach project where we said, okay, for that particular electroactive polymer, can we do something interesting? So we put together a team of undergrads and middle high school students, and they built this. And that was very impressive, I guess, at that time. That was meant to be a joke. Of course, we evolved over the time, and this one actually has a smoother motion and swam in my big tank. From there on, we have built different prototypes, and also we start to look into environmental monitoring applications. So everything happened kind of incrementally, gradually. So there really didn't have a lot of jumps during these transitions. And later on, we actually started working on so-called gliding robotic fish, because once we are serious about environmental monitoring, you want to be able to operate in the field for a long time. There, the energy efficiency is very important so that the battery life can be extended much longer. So the gliding robotic fish is actually an onboard glider plus a fish. So it has a tail, it can swim, but also it has a gliding mechanism to realize that very energy efficient buoyancy-driven motion. Because I gave a talk here 3 years ago. So I will not spend a lot of time talking about this, but I want to show you some of the applications that we are pursuing. One is monitoring the harmful algal blooms in the lakes. That's actually as a growing problem worldwide, and particularly for areas like Ohio and Michigan. So we're able to use a robot to sample the concentration of these variables at different locations and at different depth. The other interesting application is tracking fish movement. So the robots are basically tools, right? They're platforms. And you can mount different sensors so that you can do different things. In the case of fish movement, people are interested in that because you want to know where like invasive species will hang out. Okay, what are their migratory patterns or spawning patterns? And then accordingly, you will be able to set up traps. For example, if you are dealing with like sea lampreys, which are a notorious invasive species for Great Lakes, and if you know where they are, then you can put up control mechanisms at the right places. Right? So sea lampreys are essentially the vampire of the Great Lakes. They will find and attach to host fish and grind on the skin. So they will attach and then grind until there is fluid, body fluid will coming out to the sea lamprey, and they will feed on the fish. And Canadian government and the U.S. government spend millions of dollars every year dealing with this problem. So to help out, we kind of propose to use gliding robotic fish to help track these. This is based on something called acoustic telemetry. The idea is you will implant a spy device, in this case acoustic tag, into the fish, sutured up, and let the fish go. In most cases, the fish will be doing fine, and they will hang out with their peers that are untagged. By tracking these tagged species, you make an assumption that you also understand or track the movement of the general population of that same species. So to do that, so basically we have a robot mounted with these particular acoustic receivers to detect such tags. And here is one video we took last year. So I'm trying to speed up, but I cannot find my bar here. Alright, so I think better for me to open it in a separate place so that I can have better control. I know you like music, but I also want to talk a little bit. So it has, if you guys see here, this big thing here is actually the acoustic receiver that it can detect the signal from the tagged fish. And you have also seen multiple other sensors that measure water temperature, dissolved oxygen, light radiation, chlorophyll, and actually harmful algal bloom as well. So now it shows different motions like gliding and swimming. It has being able to detect some of the test tags that we put in water and get us the range data and so on. So that was
what is the frequency or sort of rough duty cycle over which you say switch from glide down to glide up?
Typically, in this case, we're gliding about 15 feet. It takes about 1 minute down, 1 minute up. If it's deeper, then basically it will be proportional to the depth that you will be diving.
And what's the range over which this receiver can track the tagged fish?
It's about 1 kilometer.
1 kilometer.
Yeah. So you don't really have to be swimming side by side with the fish. Again. So we actually recently did a second test, or a second prototype. Now it's a different, it's a yellow. And we all look like just coming from space, but it was actually the protocol of USGS, because that's our collaborator. When water temperature plus air temperature total is less than 100 degrees, you have to wear these jumpsuits. So the thing here is, I don't know whether you can see, the fish finally has eyes, which actually I like. But one reality here, especially for those people who are struggling with your research, is that it's not always a monotonic function, right? You may feel like you're always making progress, and actually a lot of times you have to be able to sustain setbacks. Like even this very field trial, we almost lost the fish, and it's what these guys are doing, right? We're trying to actually find the fish. So, fortunately, we're able to rescue it at the end, but this is just part of life. Not only building robots, of course, there are a lot of interesting control problems. I understand this is also a CDS lecture. So for this particular problem, we are actually interested in when you have multiple of these robots, you get detection from a fish, and you get detection from fish, but at different times. That's what we call time difference of arrival of the signal. With that, you can compute where actually the fish is, or localization problem. We are interested in doing it in a dynamic manner and in a distributed manner. So we actually formulated a networked standard time and filter for doing this. And there will be a question about what kind of network connectivity you would need in order to, for every robot, be able to actually correctly estimate the location of the fish. So other than that, we also are interested in how you balance the movement energy with estimation performance, because you could choose always go with the fish to have good performance in terms of estimation, but you spend a lot of energy. So what is the trade-off there? So these are just a few sample projects, I would say, that we have been conducting over the years. And now let's switch to the main topic of the talk today, which I have about 20-25 minutes. So this is about hysteresis. Hysteresis, of course, everybody here will have seen this from your high school physics, ferromagnetic material. You have this kind of loop between the magnetization and applied magnetic field, right? So essentially, I heard in Greek, this means like lag behind. Is that true? Okay. So that's actually how the word started. So basically, if you kind of move from this side to this side as input, okay, you follow one branch, and when you come down, or when you reverse input, you follow with another branch. It's almost like the output is lagging behind the change of the input, roughly speaking. You have to be careful though, because take any linear system, a second order, first order system, if you run the input and output, you plot the input and output under a harmonic, like sinusoidal function, you will get a loop. But we don't call that a hysteresis. If you want to check, you have to run the test under quasi-static input. Okay, so otherwise any phase shift between input and output will create a loop. But that's not the case, right? So really, I'm going to show you in the next slide a number of other hysteresis phenomena from different areas, and the origin of all of that is because there exist multiple we call metastable equilibrium for the system, because the system is composed of millions or billions of small components. Could it be molecules? Could it be individuals and companies for society? Okay, depending on what you're looking at, such a huge system will have a lot of equilibrium, and which one you will be parked at, it will depend on the input history. So that's why it is showing up like that. So hysteresis is everywhere. Maybe a little bit of exaggeration, but not quite. As I just said, if you look at ferromagnetic hysteresis, here is, if you're looking at the mechanics of materials, the stress and strain curve, right? You have this kind of loop. When you load the material and unload, you get this kind of loop behavior. This is about soil science. When you look at water tension in soil versus the kind of suction pressure around it, right? So you will see these loops going on. The last one is a little bit kind of outlier. This is called short-run Phillips curve in economics, which shows the relationship between inflation at a particular time versus unemployment rate. Now, typically, that's inversely correlated because when you have unemployment rate high, the inflation, because the economy is not going very strong, so the inflation is also typically down, and vice versa. But it's not quite a single monotonic decreasing curve. You will see, of course, a lot of complicated things, but you can notice there are small loops like this, showing the histories there. And as I pointed out, that's because the society is composed of so many individuals and companies and other governments and so on. So when you put everything together, that's a huge system that has a lot of equilibrium. So histories, particularly for us, is the interest comes from so-called smart materials. The very first slide about negative shifting material is one example. Piezoelectric materials, shape memory alloys, the electroactive polymers, these are all smart materials. They are composed of different molecular structures, right? So they will histories will show up in a very predominant way in all these materials. The example I'm going to give here is vanadium dioxide, which probably is not very familiar to many of you. It's a relatively new smart material. It's multifunctional because it's not only mechanical, thermomechanical coupling, it has also other couplings, as I will explain. So essentially, this is two phases. Just like shape memory alloys, it has solid to solid phase transition. So this is one of the phases called monoclinic phase. This is at a low temperature. At a higher temperature, typically beyond 68 degrees Celsius, you get sort of tetragonal or rutile phase, where everything looks more squared, right? And this is typically done by changing the temperature, as just mentioned. It could be laser, like opto thermal method, by shining laser on this, or apply current to the material or to some heating elements. And you will see abrupt changes in electrical, optical, and mechanical properties, as I will show you in a couple of slides during this transition. So this has been mostly collaboration work with a colleague. Actually, he does MEMS, Nelson Supervita. So his group has fabricated a number of devices. Here, VO2 vanadium dioxide is deposited on a silicon cantilever. And when it's heated up beyond the transition temperature, the structural change in the crystal will cause kind of contraction at the interface of the VO2 and the silicon. So it will generate basically a curve, kind of bending motion. And this can be seen from here. So it's an SEM image at multiple frames, and you can see that bending there. And they have also created a MEMS mirror device where you have 4 of these actuators on 4 sides, and you can actuate them differently to either do pumping motion, like up and down, or tilting motion. And this is fun. So in this case, this is going to dance. So I don't know whether you can tell, there are 2 actuators here, and it's dancing with the music.
So it's driven by thermal means? Right now, in this?
I think it's just because it's a laser shining on each of these, depending on the music. So anyone knows the music? You like the music? Please. It's an MSU fight song. We'll be hosting Maryland tomorrow for football. Don't ask me who I'm going to root for. Of course it goes. So that's VO2, and it's actually pretty promising material for MEMS and.
This talk is being videotaped.
Oh, I'm sorry.
They're going to see it also.
It's okay.
So I have a question. So the phase change, response time, what is it like? I mean, in the sense that how fast you can drive the lasers.
It's actually pretty fast, probably nanoseconds. But much of that is limited by the heat transfer. Laser is faster. If you have just like dual heating, it will be much slower. Like maybe we'll get into an scale is probably maybe hundreds of kilos.
So this is spot heating on the spot heating by laser spot
Right.
on the cantilever.
Right. Right. But for MSAG, for the dual heating, you have these wires.
Sure.
But the controlling frequency should be on the next structure, right? That's the one that controls how fast you can.
Yeah. Yeah. But it's limited by the actual mechanical bandwidth. Is
Energy on the
yeah. Right. Yeah. So yeah, there is limitation about the mechanical bandwidth, how fast is this resonance, or what's the resonance frequency of this cantilever, but also how fast is the thermal thing.
How well can you predict this from models?
Depends. For usually control-oriented model, that's actually reasonable as well because you're doing feedback.
So the structures you saw that your predicted design are these forms predicted or they're done by trial and error in the lab?
More or less predicted plus some trial and error. We use like multiphysics simulation to see what's the temperature distribution, how fast it evolves.
What do you use for it?
Because we are using thermal.
I don't know, what do you use?
I think console. Ansys probably also part of that. So you will see optical property changes. What you're seeing here for VO2 during the transition is here you have optical transmittance for infrared. So if you look at this material, of course not visible, but infrared, it is actually transparent to infrared at low temperature, but when you heat it up, it becomes opaque. This is the electrical resistance. It changes about 2 orders of magnitude from low temperature, which is almost a semiconductor, and to high temperature becomes a metal, essentially. And that's a big change there. And of course, the bending curvature will change with the temperature. But in all these graphs, you see loops. So that is kind of my pitch for why this problem is important. Once you have these hysteresis phenomenon, it causes a lot of problems in terms of modeling, in terms of how effectively you can control this. Even though recently we have done some work in exploiting the hysteresis to program the actuator so that you don't have to use as much power in order to switch between different states. Unfortunately, I won't have time to talk about that.
So hysteresis does not always have.
Yeah, exactly. Yeah. So that's the last point I was saying. I actually exploit it for some actually beneficial application. So modeling hysteresis. So I'm not going to give you hours-long lecture on hysteresis. I would love to, but we have very limited time. So what I want to do for the rest of the talk is to give you a small problem, and hope I can explain the problem clearly so that everybody gets something out of it. How we model that? Of course, you can use physics to model what's going on inside the phase change and so on. But very popularly, people have adopted so-called hysteresis operators, so that they can use the same set of operators to model different materials or different areas, hysteresis from different areas. So the idea is you can put multiple very simple hysteresis units, and then you weigh the superposition of these. And of course, you can have different basic units, but this example here is called play operator or mechanical backlash. Okay, if you have a gear, you'll feel that. It doesn't move until you hit on this side. If you reverse, it doesn't move anything until you hit the other the boundary of the other tooth, right? So if this is the input, and if you are here, when input is increased, during the backlash, you don't move. You hit the other side, you go up with it. Okay, think about the gear. And then if you reverse, nothing would happen in terms of output until you hit the other side. Okay? So this is called play operator, with this parameter R basically defines the width of the hysteresis loop. The R here we'll call it the threshold. Sometimes people call it threshold, sometimes people call it radius. So let's call it radius. And then based on that, you can construct a more complicated behavior using multiple of these units with different width. So you will see different R there, different width, and also you weight them. So you have different parameters to account for the contributions of each. So that's called Prandtl-Ishlinskii operator, sometimes called PI operator. The downside of this is actually it's very symmetric. If you look at this behavior here, it's always autosymmetric. So whatever you can come out of this, it will be asymmetric. And also it does not saturate. We have larger and larger input or lower and lower input. It doesn't saturate. And these are the problems people actually often encounter for modeling hysteresis. Being asymmetric and being able to allow saturated behavior. So you can basically make modification of that to get so-called generalized PI operator, where you see this is a generalized play operator. Okay, I want you to focus on the dashed line curves. Forget about this outline for now. Now you have two envelopes, kind of two curves on the left and on the right. Okay, these are so-called envelope functions. And when I don't have any radius, I equals 0, that's what you see for the dashed line curve behavior. Okay, so you would so that's the case. Now when you have a radius r, okay, I'm going to inject radius r. You basically would push this curve up by r, push down this curve by r. And now if you look at these two envelopes, that determines the boundaries of your backlash movement. Okay, so for example, if you're here, increase, you're going to get it here, and you will climb up on this right curve until you reverse, and you'll come down on the left curve. Okay, so and that way you complete a loop there. Now, same idea. If you combine multiple of these with different R's, and you can create so-called generalized GPI, generalized Prandtl-Ishlinskii operator. Mathematically, you can write it as the summation of, kind of weighted summation of these different units. You could also do a continuum version. You can do an integral of all possible radius values with some weighting function. But I'm not going to talk about the continuum version in this talk. So, having said that, now where is going to be, so the talk is about model reduction. In system theory, model reduction means if you have a very high dimensional system, you would like to reduce to low dimensional system, and hopefully being as close as possible to the original system. So here, what do we mean by reduction? As you can see here, we have a lot of these. I'm not going to go back. We have a lot of these so-called generalized play operators, and I claim that's your complexity, or that's a system order, because every play operator has a kind of state variable, which is its own memory. It's a dimension 1. Okay, so when you have n of those, your dimension is n. So it determines number of state variables or system order, and also it determines the number of parameters we have identified, basically those weights. And also the complexity of controlling such systems. And a popular approach to controlling hysteresis systems is so-called inverse compensation. So assuming this is your hysteresis module, typically it's coupled with some other dynamics, and your controller oftentimes will look like this. You have inverse compensator, which will cancel out this, and then you are just dealing with this portion, the regular dynamics, with some controller. Right? So that's a rough paradigm. So to construct the inverse, it's also very complicated oftentimes. Fortunately, even for the GPI operator, it has an analytical inverse, which means you actually can run, you don't have to do recursive calculation, but still, it is also another GPI operator, which with the same number of play operators. So really, if I can get this play operator number down, I can have similar system, right? So here's a model reduction problem. Given such an operator with n, capital N generalized plays, can you find an operator with only n plays? M, of course, should be less than n, that best approximate makes the original operator. I said best approximate with quotation marks because I even didn't say what would be optimal. What would I mean by that? So hopefully we can get to that here. So in this case, I'm just showing you kind of a graphical example. So we have n of these plays. I'm only plotting their radius values from R1 to Rn. so the width of the different plates. And the vertical shows the weights of each. Okay, so some are very low, some are actually pretty high. So the idea here is, can I essentially group these guys into M clusters? Okay, of course, neighboring elements will form clusters. So M clusters, and then for each M cluster, I will define another new plate operator. That's the idea. That's the concept. Okay, I've not told you what's the solution yet. That's kind of part of the problem formulation here. So that's what I'm saying. You can have, let's say, group these guys in a consecutive manner, and you can divide using beta. I'm using beta here to indicate the boundaries of each cluster. Beta 0, which will be 1, beta m, which is the largest one, will be Rn. In between, you have these guys to keep track of the boundaries between different clusters. So for each cluster, I will then define a single plate operator to represent them. Okay? And here I have a specific way of doing that. Once I have cluster, I have a specific way of doing that. Essentially, the radius, or the kind of where I'm going to put this within this to represent these guys, is due to a weighted summation, or weighted combination of these different original i's. So who is more important, who is more predominant, I'm going to put this closer to that. Right? So that's the idea. So this is the individual weight, and this is the total weight of that cluster. Okay, so calculated here, total cluster. So S sub k is the elements of this kth cluster. So from, for example, beta k minus 1 plus 1 to all the way to beta k. So that's the idea. And then how about the weight? How high should I make this? How important? Of course, that should be the total of them, because you want ultimately the weight is going to be the same, right, as original.
Okay,
So
can you then show that the output of the cluster?
I'm sorry.
Can you then show that the output of the cluster as originally headed in the system is close to the input output of the single operator? And what is the metric of that?
Yeah, good question. I'll show you in the next slide. So the question is exactly that. Now you define this. You divide into clusters and you define these guys. But how do I quantify how good this is when I use one single operator to replace all these guys? What is the loss of information in this case, or cost? So that's a question. We are employing the idea of entropy here. So of course, I assume everybody knows about entropy in this room. For discrete random variable with probability mass function, Pi, and entropy is calculated this way. Right? It's just definition. And more importantly, we know when is the entropy going to be largest? Everybody has the same probability, right? When is the entropy going to be smallest? Well, there's only a deterministic outcome. Okay, so there's one possibility where it's actually probability 1. Everybody has up to 0, right? So if you think about that, in this case, if I have in a particular cluster, I only have one element, you are not getting any loss, because I can use that one element to represent the whole cluster without any loss. On the other hand, if your cluster has quite a few with almost like a uniform distribution, then I know if I want to represent it, I will struggle. Where should I put my representative, right? So you would expect error will be there. So just inspired by that, we said, okay, let's define the entropy, or let's define the metric by using the entropy of that cluster, basically the weights of that cluster. So that's essentially the idea here. So, of course, the initial weights are not normalized to 1. So we have to perform the normalization by the total weight. So you get this normalized version, and then calculate the entropy. And since we're going to do an optimization of the entire spectrum, so we have to also put in the cost for the total weight. So, for example, this cluster it has its entropy of the normalization, but also we have to account for the fact that either this cluster as a total has a lot of weights in the whole operator or not. So that's why we put this pk here. And the last term, you don't have to worry too much, because we're going to just further to emphasize that your centroid, which is the representative position, how far is it from different individuals, and you can weight that with their own weights, individual blade weights, to further define it. Even without the last term, actually, the algorithm is defined.
So how, and I don't understand, how do you deal with that? The way to understand, but they will do the R's, but because you have different R's.
Yeah, so different R's. So
Just the clustering?
just no, once you have the cluster, basically I'm saying, okay, now I will add another kind of modifying term there, depending on like, if there's only one in the original cluster, then the difference is 0, right? So there is no loss there at all. But if there is, and then like this guy, there is some distance, there's some distance, so you look at the distance weighted by their own weight to further factor that, and basically your choice of that particular representative will have what kind of impact on the type error. Okay, welcome. So once we have that, we can now look at how you solve the problem. Okay, we have about a few minutes. So that's one cluster, but then for all clusters, I can look at what I can add up all these different clusters costs, or I can look at the maximum. Actually, it doesn't change the algorithm much. So here's a small trick. I hope people here can appreciate. When I reformulate this problem, again, this is actually a pretty simple problem, but I think it's a nice small trick here. This is a graph we're looking at. So I'm actually going to change this total optimization problem into optimal control problem. If you define, these are the boundaries of clusters, so I'm going to define my states and a control and a dynamics, right? That's all we need for a dynamic system. So I'm going to define these guys as my states. So xk is going to be beta k, and the control is only going to be the difference between these guys, essentially the numbers of these, how many of these in each cluster. And then dynamics is very simple. First order system, right? Xk is basically xk minus 1 plus the input. And then the cost function is going to be adding up all these. Of course, you can do maxima as well. So if you look at the cluster cost, as we just explained, your cost or information loss or cost for that particular cluster, essentially in the optimal control problem here is a stage cost, is only dependent on where you start, basically the set, right? And where you start and what is the stand. So that's actually what is your initial state value and the control. And then, of course, last one, you don't have any control here because it's automatically set already. So you actually have the terminal cost. That depends on the starting point of that last cluster. So by this point, I think actually my talk is done because the rest of it is straightforward. We can run dynamic programming to solve it. Right? So you can consider this is standard stuff now. Sequence of n-1 optimization problems. Kind of depending on where you start. You start from k through n-1, or k can go from initial point to the almost last point. And then you can define the value function for each optimization problem. That will be the best control you would have for that particular problem. And then from there, you how to calculate, right? So you do backward recursive calculation. You start off from the last problem. Okay, if I only have to decide one partition, what should I do? Right, the last problem. And then you move backward. If I have to do two partitions, okay, that's iteration of your value function. And during that process, you also generate the optimal control feedback. I say feedback because it basically says for whatever current starting point, what would be my strategy? It would be different. Of course, in our problem, the initial condition, the whole problem has a fixed initial condition, which is beta 0 equals 1. So you automatically get the whole the solution. And you can easily analyze the complexity of the algorithm. Basically, we use the number of evaluations we have to do for how the information loss. So it turns out to be this, which is pretty decent, okay? Because it's essentially linear, bounded by a linear function of n, how many clusters you want. On the other hand, if you do exhaustive search, which basically says, okay, I have n place, I want to pick m, and I can, of course, look at all possibilities of these m out of these m, right? So that's just picking m out of m, and that is your complexity right here. Which if you cannot see why this is more complicated than it's just plugging some numbers, you will see that actually it's a dramatic difference. So we evaluated this with simulation and experiments. So the simulation here is, okay, let's look at 30n. And I would like to cut down to 6. And I will look at different different distributions of weights of the 30. And we evaluate on a particular input. This is kind of damped oscillation input, which is actually often used in parameter identification for Hysteresis operators. And you would get output function. If you plot output versus input, you would get something like this. A lot of inner loops and outer loops, right? So this next loops of the hysteresis. So we will conduct reduction. And then, with the same input fed into the reducer model, evaluate what's the corresponding output. And then we're going to compare with the original output, look at the mean square error of that difference, or mean square error there. And then we're going to normalize it further by the range of the output, just to compare between different distributions, so you don't get, numbers more in the same range. So here we can look at the 4 different distributions of the weights. This is a fairly uniform weight. This is a single peak, double peak, and more random case. And it turns out, for the uniform case, I'm comparing with so-called uniform clustering. So basically, you just do 5, 5, 5, 5, right? So that's what people typically do, is just have uniform spacing between those. And then the error here is going to be 70.75%. If you do entropy-based, error is going to be the same. Why is that? You cannot do better than that because it's already a uniform distribution. But no matter what you do, it's going to be this. The optimal is going to give you the same results, right? However, if you have a distribution like this, okay, the error here is like 20% of if you do just a uniform distribution. Okay. For this case, you have also almost half of the error if you do uniform distribution. But if you do entropy-based optimization, right, it's basically 100% improvement in performance. When you have really random case, it turns out the error is fairly similar. You actually notice that our optimizer method produces more error. How do you explain that? It's slightly bigger. Well, optimal should always give you the lowest error, right? No, because I'm not evaluating with a different metric now. The optimization is based on the information loss of the weight distribution. The evaluation I'm doing here is using the input and output on a particular input particular input pattern. So that's not, I wouldn't say always expected, but it's explainable. Computational complexity. The blue curve is exhaustive search. The time you actually spend, and this is in log scale of the number of evaluations. So this is a linear scale. And you can see the big difference between the optimized case versus if you just do an exhaustive search. Finally, we have roundness on the experimental curve of this VO2 patch. So in this case, it's not a MEMS actually, it's just a positive VO2 patch. We measure the temperature, change the temperature, and measure the resistance. Right? So this is already, resistance is taking like a log function, and you'll get data there. And then we fit that with operator with 30 plates, okay, 30 basic units, just like what we did in the simulation. So you kind of see a good fit there. And then we start to compare with the uniform partitioning as well as optimal partitioning. Right? So you see these blue dots are the original weights across 30 of these plates. And this is the final selection by the uniform partitioning. Okay, don't be confused at why the uniform partitioning doesn't produce a uniform space vectors, because we're partitioned there, but then remember in every case the actual location of the representative is determined by the weights. So it's not exactly like that. But you see that the actual partition is different with the optimal method against the uniform method, the error also is about 30% less in this case. Finally, acknowledgement. Jing it was my student who actually now is a postdoc at UC San Diego. He actually is on the market for faculty position this year. Nelson is my colleague, and Emmanuel was a student of Nelson. And this is basically the paper from Dynamical published in 2015. If you are interested, I will be happy to send the link. Thank you.
Thank you.